So we've discovered the Maclaurin series for sine, and that is here. Sine of x equals this sum right here. Pretty remarkable fact, and we're going to sort of explore some of the niftiness of that. So first of all, we're going to use the Maclaurin series to find the sine of 1, because that's what these series are for, is how do you find something like the sine of 1 radian, or the sine of 5 radians, or whatever. All right, so what you do is you set up this sum. So this is just this Maclaurin series, and what I've done is I've substituted for the x, I've substituted 1. So for the x in this sequence, I've substituted 1. And then since 1 to the 2n plus 1, well, 1 to anything is just 1, so I just simplified that and made it 1. All right, so this sum is going to tell me what sine of 1 is. So I can just calculate that, and let's see, I did that. Find it here in my calculator bag of fun. So yeah, so here is the sine, the sum from x equals 0 to 15. So I've only done 15 terms of the sum here, 15. Negative 1 to the n, I have to put x because that's what the calculator speaks. And then just 1 over 2x plus 1 factorial. The factorial is over here, you can't see it. But by the way, you get factorial on your calculator by doing math, and then you go over to, it's called statistics. I think it's under statistics. Let me just pop one in here. Yeah, all this stuff here. So if I want to do 5 factorial, I go 5, and then I go math. It's under probability, and then I scroll down here to number 4 is factorial. So then it tells me 5 factorial is 120. All right, but back to what we were talking about, which is what is the sine of 1 using 15 terms of the sequence. Well, here's 15 terms of the sequence. I get 0.8414709.848. That's the sum of the first 15. So this is an infinite sum. This is the sum of the first only 15 terms. And if we look at what the calculator says the sine of 1 is, it is exactly the same. It's exactly the same. So all that means is that it's accurate to within 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 decimal places. So they probably diverge someplace later. And ultimately, when your calculator does sine of 1, it's also doing a Taylor series. So you're really just comparing one Taylor series against another. But there are ways to limit the error that you get in calculating value using finite number of terms of the infinite sum. That's what we're really doing here. We're estimating the value by using a finite number of terms. So yeah, what do I got next up here? All right, so what if I wanted sine of 5? All right, how about sine of 5? Right, so what I would do, so this value that I'm putting here is the x here. So I have sum from n equals 0 to infinity of negative 1 to the n, and this time I'm going to have 5 to the 2n plus 1 over 2n plus 1 factorial. That's just subbing a 5 into this equation up here. All right, so I already did that, and here it is. The sum, I did 15 terms again, negative 1 to the n and my 5 to the 2x minus 1. This is how I know I'm doing sine of 5. And when I did that sum, I got negative 0.95892424747. And when I actually did the sine of 5, how close is it going to be? Well, it is exact to within 10 decimal places again. And this is again with only 15 terms of the sum. So I went on to say, let's look at the sine of 10. All right, so I replaced the x with 10 in this calculation, and I got negative 0.544127277, and then I compared that with sine of 10. And this is where I first start to see it be different, 5440. Right, they don't quite match in that 1, 2, 3, 4th decimal place. I'm still only using 15 terms of the series. I could use more terms of the series and get this out to 10 decimal places. But what's really happening is as I get farther from 0, it's going to take more terms of the series. So if I get really far from 0, so here's using 50 for the x, all right, using 50 for the x. The sum gives me negative 4. Well, sine can't be negative 4. That's totally, totally wrong. So I didn't even have to look at the sine of 50 to know that it's not going to be negative 4 because sine of 50 can't be negative 4. All right, so what's happening here is that the series becomes increasingly inaccurate as I get farther and farther from 0. So now I'm going to show you a really nice visual as to why that is the case. So here I have sine of x. All right, so there's a nice graph of y equals sine of x. And down here, I have x, so that's just one term of the series. I have x minus x cubed over 6, that's two terms of the series. X minus x cubed over 6 plus x fifth over 120. Three terms of the series, four terms of the series, five terms of the series. Remember in the calculator, I used 15 terms of the series, but there's no way I have the patience to write all that out. So let's just look at what each of these look like. Here's our first term. So it doesn't look very much like sine, but it is at least tangent and shares the same y-intercept. Then if I go to the next two terms of the sequence, here's two terms of the series. So look, it's a cubic, so it can have two turning points, and they sort of match where the max and min of the sine are. All right, and then I go to my fifth degree polynomial. So every one of these is a polynomial, by the way. So I'm approximating sine with a polynomial. See how the fit's getting much better? Because I have a fifth degree polynomial, I can have 5 turning points. This only has 4. I think something happens in there. That's right. I can have 4 turning points with a fifth degree polynomial. 4 turning points. So then when I go up to 7th degree, which we have here, now I can have 6 turning points. Although it sort of doesn't, like, it can have 6 turning points, but it doesn't have to. And I think it's sort of fitting more with the particular exact concavities at each point. So it doesn't have to have those 6 turning points. This one has 1, 2, 3, 4 turning points. It could have up to 8, but you will see sine has infinitely many turning points. So in a way, I'm going to have an infinite polynomial to meet it all. But you can see how these approximations are starting to really fit nicely within the sine. Now, I think I'm probably going to have you guys do some of these both as homework and for a project-y thingy that I'm thinking about. So I want to show you some nifty things that we can do in Desmos. So one thing that I figured out we can do is, I don't want to have to write this whole thing again. I just want to add one more term. So if I punch the equation I want to work on, and I hit the little gear up there, see the little gear? Hit the gear, and then I get all these options, and one of them is duplicate. So this little double page here is the duplicate, and that just duplicates. And then I can go to, now I've got to the exact same thing again. And now I can just add my next term, which is minus, we want x 11th, so x to the power 11. And I arrow over to get out of the power, divided by, now I have to do 11 factorial, so where is that? I go 11, you go to the keyboard, ABC, you hit that ABC, and there's exclamation point right there, the exclamation point right there, and that's just your factorial. So you toggle back and forth between the numeric keypad and the ABC keypad using the ABC button, so we get the factorial there. All right, and that's my next polynomial, and you can see how it's fitting better. I can turn them on and off just by clicking on the little graphy circle-y thingy here, supposedly. There we go. So that's my 11th degree polynomial fitting into sine. You can see how it fits better and better. But you can also see that the farther I get from 0, like it starts to completely go off, right? So when I was estimating x of 50, all right, I was way over here doing sine of 50. So it was completely off. It was -4, so it was down here, all right? But you can see how what's happening as I include more terms is I model more and more of the behavior around 0. So the terms around 0 are getting more and more accurate, better and better, and the terms that are farther from 0 are getting more within the realm of feasibility. So you can see that to get anywhere close to sine of 5, I have to have that 11th term in there. Fortunately, I did 15, and it was pretty accurate.